Okay, so it's just a bit after 3:30, so let's pick up where we left off. So right before we took the break, we spent some time working through these exercises. So we had 5. Did anyone get all 5 of them? A couple people. How many got 4? 3? Okay, cool. So let's spend just a couple minutes going through these. By the way, if you're looking for the answers, I'm sorry, they're sort of hidden. And the idea of hiding those is, so you spend some time working on them, not just to sort of click through the next one. But you can see on the next page, there's this :play guides.neo4j.com reco answers. But that doesn't do anything. So you actually just need to append the number of the chapter that we're on, .html, and then that will give you, maybe not. Oh, I see. It's not that. It's reco-oscon-answers/1.html. So sorry about that. So again, just take sort of whatever is after this /reco-oscon and add answers/ and then the number of the chapter we're on .html, and that will give you the answers for the exercises. Okay, so let's go through these really quick and then pick up where we left off. So the first one, which is the most difficult one, what's the most popular topic? So if we think of the data that we're interested in here, most popular topic, well, what does that mean? Well, that means that there are a lot of groups that have an outgoing has-topic relationship to some topic, right? So I don't know, like open source is going to be connected to like 200 groups or something like that. So what is the data that we need to look at to answer that question? Well, if you think of how we want to traverse the graph, we want to go from a topic, we want to follow these incoming has-topic relationships and count the number of these has-topic relationships for the topic. In graph terms, this is called degree centrality, or just the number of relationships that a node has. So centrality is a measure of like importance or something like that in the network. There are lots of different ways to measure centrality. Like PageRank, for example, is just an eigenvector centrality. So degree centrality is just counting relationships that are connected to a node. Anyway, so we say, okay, so match on every topic and follow this has-topic relationship. And we know that on the other end is a group node, but we don't care about the node, so we don't have to specify a label or bind that to an alias or anything. Instead, what we want to do is return topic name. And now anytime we return something along with an aggregation, we get an implicit group by. So here we're saying return the topic name, group by topic, count the number of paths for that topic, and then order by that count descending. Right? So we sort of have this implicit group by topic going on there. And, oh, I was close. Open source is the most popular, but only 105. So 105 groups have the topic open source, 75 have big data, software development, and so on. So we can see the most common topics. Okay, so that was by far the most difficult question. If you got that, then you should be in good shape for the rest of these. So the next question, which group was created most recently? Well, if we look at the data, we see that we have a timestamp created, which is just a timestamp for when that group was created. So we can just match on every group. And then when we return the groups, just be sure to order by the created property in descending order. If we do a limit 1, that gives us just one group. So Jamstack. What's that? Does anyone know what Jamstack is? No? Some hot new stack that we don't know about? Okay. Anyway, so Jamstack meetup group was created most recently. So that's the hottest, trendiest meetup group in Austin, apparently. Okay, so the next question, how many groups have been running for at least 4 years? So if you notice, if you look at the way that we're working with time, it's kind of a pain. We're just using these timestamps, which are longs, right? So milliseconds since the epoch. So Neo4j doesn't have a native date time type yet. So instead, the common way that we work with date time is with a timestamp. We won't be able to cover it today, but if you work through some more of the examples in this guide that we're going through, there's a section on procedures, so user-defined procedures, user-defined functions. There are some of these, so libraries we can import that make working with time a little bit more straightforward. But anyway, so that's why we have to do this sort of find the difference between now and when the group was created and go from milliseconds to seconds, days, to get years where that's greater than, where that difference is greater than 4. And we can see we have 37 groups that have been running for at least 4 years. Okay, so the next one, find groups with Neo4j or data in their name. So if we look at the Cypher ref card, which we should, which hopefully I'll be using. If we look for string matching, we can see we have starts with, ends with, and contains. So in this case, we want to do a contains search for Neo4j or data. We can see we have quite a few. We have 31 groups. So note that this is case sensitive. This is a case sensitive comparison. If we wanted to do case insensitive, we'd have to do something like convert all of these to uppercase or something like that. Right, something like that. That works. Okay, and then for these groups that have the name Neo4j or data in the group name, what are the distinct topics for these groups? Yeah?
Question regarding the contains with versus like using the regex string matching that I saw. Is it just that it's slower or
yeah.
anything else really besides that?
Yeah. So the question is regarding the difference between doing a contains search, string comparison search, or using a regular expression. So we can use regular expressions with Cypher. The biggest difference is that if we have an index on the property that we're comparing, in this case the name property on group, which we do, if we have an index, then we'll use it with a contains search, but we won't be able to use an index with a regular expression. And by the way, while we're talking about it, we can figure out under the hood what's going on by starting any query with explain or profile, and that will give us this query plan So every Cypher query is converted into a series of database operations. And so when we want to tune a query for performance, it's often very helpful to look at the execution plan to see the actual database operations that are going on. So in this case, we'll add explain, and we'll see the query plan. And we can see here that we have, for the planner, is we have a cost-based planner. And what that means is that because we have a cost-based optimizer, we take into account the state of the database at that time to come up with the optimal execution plan. So in this case, we're actually doing a scan and then a filter, because with this super tiny data set that we're looking at now, the query optimizer thinks that that's actually more performant than doing an index operation. Anyway, so just wanted to talk about sort of the tooling that you have for tuning queries. There's a whole section in the manual that talks about when we're tuning sort of different database operations to look for and that kind of thing. Okay, so we found groups that had data or Neo4j in the name, but now we want to know what are the topics that show up most frequently for these groups. Well, this is going to be very similar to what we did when we were answering the question of what are the most common topics for the overall data set, except now essentially what we're doing is we're filtering groups that only contain these words in the name. And we come up with, no, we're not ordering those. Let's order these. So if we order these, data analytics is the most popular. It shows up on 24 out of, what were there, 37, something like that. Big data analytics, and so on. Cool. So that was our first little exercise. Now that we've imported some data, we've learned a little bit more about Cypher, hopefully. Now we can actually answer our original question, which was for members of the graph database Austin group, what are other similar groups that we can then recommend to members of the graph database group that they might be interested in. So what does this query look like? Well, we start off by matching on all groups where the name contains graph database or Neo4j. And that's sort of just for simplicity. We can verify that, yep, we only get one group. So this is graph database Austin. That's one group. We can see the topics that this group has. And we can traverse out from some of these topics. So like here's data visualization. We can see the other groups that share data visualization. The topic Neo4j, we can see other groups that share Neo4j. And so really what we want to do is sort of expand out on all of these, do some aggregation to get the count to see what groups have the most topics in common, and those are the ones we're going to recommend. So we do this filter, find groups where the name contains graph database or Neo4j. Then we traverse out from that graph database group to find the topics that it's connected to. Then from those topics, we traverse out again to find the other groups. And then we said when we return something along with an aggregation, we get this implicit group by. So we do a group by the name of the other groups. That's essentially the group that we're recommending. And we count the number of topic nodes. So for each group that we found that shares at least one topic in common with the graph database group, how many topics does it have in common? We use that as sort of a score for the recommendation, and we return those groups ordering by the number of overlapping topics. And we can see that the Austin Graphs Data Processing and Algorithms group is our #1 recommendation because it shares 5 topics in common. Big Data Developers also has 5, so those are sort of ranked the same, and we can see the topics that they have in common. Questions on that query? So note that there's a lot of problems here, right? We're not normalizing. If there's some group that has just a whole bunch of topics, it's going to be every time our #1 recommendation, but that's not necessarily very useful. So this is just sort of our initial simple approach. Yeah.
So far, what's the benefit of using Neo4j compared to any other SQL-based database? I could run the same query and get the same answers, right?
Sure. Yeah. So the question of, okay, that's fine, but like, what's the advantage of using a graph database here instead of say like doing joins in SQL? So this is what, like 4 joins if you think you have a group topic join table. So I mean, I think like writing this in Cypher is easier to express than like joining through a group topic join table and then joining to another group topic join table. So I think that's a bit of it, is sort of the expressivity of Cypher. This data set is tiny, so the performance benefits aren't really here, but if we had some massive data set, we talked about the concept of index-free adjacency and sort of the performance benefits that we have with traversals and instead of sort of doing joins in relational databases. So that's another piece. But I mean, I think you have a good point. Like largely, there's not much going on here, given the tiny data set that we have and sort of the simple data model that we have at this point. We could write this in SQL; it would work. But I think really, like once we start to add in more complex data, so we're going to start importing members and the groups that they're members of, and events that they've RSVP'd to, and extracting a social graph from people that you've been to like multiple events with, and that kind of thing. We'll see how we can start to score our recommendations by taking different pieces into account. And pretty quickly, we're going to have a Cypher query that I don't think you would want to write the equivalent SQL of. And I think like largely, like Cypher is designed for expressing these complex traversals. So I think it's much more sort of natural to think that way. And another thing is sort of the data modeling aspect of this, right? Like this is intuitively how we think about this data. So a group has a topic that intuitively makes sense. But this idea of a group table and a topic table and a group topic join table, that intuitively doesn't really make a lot of sense, right? So anyway, that's a long-winded sort of ramble, but I think those are also some of the points to sort of get at why this is easier. Yeah?
Is the reason you don't have to specify the colon capital T topic in the middle node there? Is that just because the only entities that would have that relationship topics?
Yeah, exactly. So the question is, why didn't I have to specify this colon topic right here? So I said topic, but that just becomes some alias that this node gets bound to. Why didn't I say colon topic to indicate that that's the label? And yeah, like we don't need that, because the only thing where we have a group that has a has topic relationship to, the only thing in our data model is a node with the label topic. So we don't need to specify that. We can specify it, and we get the same result. Yep. Cool. Other questions? Yeah.
Where
where did other group come from? So other group came from line 4 in our traversal. So we started here. Sorry, I hope you can see that, the highlighting. So we started here. This is our graph database group. And we traversed out from there to find the topic nodes that are connected to the graph database group. And then from those topics, we then traversed along incoming has topic relationships to other group nodes, right? So these are now the groups that have topics in common with the graph database group that we've discovered by doing this traversal. Does that make sense? No? So let's look at it this way.
It's any name, right? It's not forms that you have to be other.
Say that again?
I think what we probably meant is that you can use any text there. Right?
Yeah, so right, so other group is just an alias, right? So I could call this my recommendation, right? And then I would just have to refer to it later on as recommendation. If I can spell, which I can't, apparently. Right? So it's just some alias, some variable that we're declaring, right? Right? But if we look at it, if we look at this sort of visually, so here's the graph database Austin group. Here's a topic. This happens to be the topic graph databases. So our query says start at graph database Austin, traverse out to the topic nodes that are directly connected to graph database Austin. So that's, for example, this one. And then from this topic, traverse out to find other groups that are not graph database Austin that this topic node is connected to. And in that case, that's these two groups, Austin Graphs, Data Processing Algorithms, and Semantic Web Austin, right? So in our query, these two get bound to this variable other groups that we're defining by sort of binding those to a piece of the pattern that we've specified. So Cypher is very much about pattern matching. So we define some graph pattern, and then we use this concept of aliases and variables to bind those elements to pieces of the pattern. Cool. So that is the end of section 1. So if we go back to our index, and if you get lost, if you lose this, you can refresh your browser, and this sort of index thing will load when the browser restarts. So let's look at the next piece, which is, okay, so we generated this recommendation that said, here are groups similar to graph database Neo4j, okay. But if you were already a member of any of those groups, it's not a very relevant recommendation. We didn't take into account any information that's sort of personal to the user. So what we want to do now is extend our data model to actually take into account some information that we have about the user. So what we're going to do, let's just skip to the data model here. So what we're going to do is now we're going to import another piece of data to extend our data model. So we're now going to have member nodes. They're going to be members of a group. And we're now going to enhance our recommendation query to take that information into account. So we have another CSV file, in this case, members.csv. And it looks like this. So, and again, the way we got this data was we started with looking at groups. Then for each group, we grabbed the topics. We already imported that. but then we also grabbed the members for each group. So again, similar to topics, we're going to have members are going to be duplicated. So I'm going to have an entry here for Aaron Tucker. He's going to show up once for every group that he's a member of, so we need to make sure we don't create duplicate members. But the data that we're working with, so we have a topics column that is a semicolon delimited list of topic IDs. So these are topics that the member has indicated that they're interested in. So we'll come back to those in a moment. Then we have the name of the member, the group ID. So this is saying that Aaron Tucker is a member of group with this ID. We have an ID for the member, and then we have the timestamp for when he joined the group. So that's the data we're working with. Let's create a constraint on member ID. So we said this is the thing that uniquely identifies our member, so we want to ensure that that remains unique. And let's talk a little bit about transaction state. So one thing we didn't really talk about too much so far is that Neo4j is a transactional database, right? So ACID guarantees in our transaction. That means that for any transaction, for any operation, like all of the transaction commits or none of it does. So if we have several statements in a transaction and we have some error, well, those statements that have run up until that point, those need to be rolled back because all of the transaction is not going to be committed. And this is very good for a graph database because data integrity is very important because of the connectedness of the graph model, so that's fine. But this can be kind of a problem when we're importing data. So any transactional system has to hold transaction state in memory sort of while you're running the queries in that transaction, so holding transaction state. And most of the time that's okay, because most of the time we're just traversing the graph. But when we're importing data, we have to hold all of that in memory. And if we're importing lots of data, this means we can get out-of-memory errors or bad performance at least. So for that reason, we can use what's called periodic commit functionality with load CSV. So if we add using periodic commit, then that means this Cypher statement will sort of manage its own implicit transactions and commit by default every 1,000 rows over the CSV file. So this is very useful when we are importing large-ish amounts of data or when we're working with very constrained resources. So these Neo4j sandbox instances are running in a Docker container with less than a gig of RAM, I think 750 megs per container, so it's not a huge amount of resources exposed to it. So in this case, we're going to say using periodic commit 10,000, so that means that every 10,000 rows, we're going to commit this transaction, and basically we're just iterating over the members CSV file. We are now using a distinct keyword to only grab distinct members, right? So we said that we have members show up once for each group that they're a member of. So that means we have lots of members repeated, so we don't need to hit the database frequently with all these members if we can just do a distinct in that batch of 10,000 and only give me in that batch of 10,000 who are the distinct members. Let's try to write those to the database. And we end up adding 32,000 member nodes. And the next thing we need to do is now create some relationships for these members. So we'll iterate through the CSV file again. We'll look up the member node. We know they exist because we just created them. Then we'll look up the group by group ID from the CSV file, and then we'll create this member of group relationship, and we'll set a property on the member of relationship that is the timestamp of when they joined the group. Cool, so we run this, and this will take a little bit because there's lots of these member of relationships, right? So if you think we had 32,000 members, and on average I'm going to be a member of more than one group. So in this case, it ends up being about 85,000 relationships. So now, if we look at our graph, let's match on members that are members of a group. Here we can see, here's Aaron Tucker. He's a member of these 5 groups. So he's a member of Google Developer Group. We can see the other members of that group as well if we traverse out, and so on. Let's create an index on member name. So we had a constraint on the ID that gave us an index on ID, but we also want to look up members by name, so we'll create an index on that. And how many people are local to Austin? A few? Okay. So if you're a meetup.com member and you're local to Austin, you should be able to find yourself in the data set. If not, you can use my name, which I show up in Meetup like this. But let's spend a couple minutes now to work through these exercises. So first of all, try to find yourself in the database. Can you figure out how many groups you're a member of? And can you figure out the topics of those groups? And then which topics show up the most? So let's spend a few minutes working on this, and then we'll go through the answers. And again, if you're not local, you can use my name, which is Lyon, and I show up for at least a couple of groups.